We have 5 interesting speakers lined up for you. The first of which is Andrew Blower, who is structural coatings engineer with Oregon DOT and also currently serving as the Western Partnership Vice Chair, correct? So Andrew's going to talk to us about replacing a double Bascule lift span control system.
Thank you everyone for attending. I'm really glad to be back here in person with everyone. Most people who know me probably know me for corrosion engineering and concrete preservation, but I actually wear many hats. And I was originally hired by the DOT to work on movable bridges. And I've been quietly doing that in the background behind a lot of the stuff that you guys have seen. So today I'm going to present on replacing a 1931 control system on a double Bascule lift span. We'll go through just introducing the structure, some of the initial conditions. We'll talk about the design philosophy and work items, and I'll go show you guys what happened during construction, shop mock-up, on-site construction, test lifts, and span commissioning. So the bridge we're talking about today, this is the Isthmus Slough Bridge, number 01132F. It was built in 1931. It's located in Coos Bay, Oregon, on the central coast. The east approach out of the frame to the right was replaced in 2010. And what I'd like to point out on this picture is you can see that it has had some straddle bents retrofitted on the west approach there, and we'll talk about that in a little bit, what caused that. For our work items, this is a very old control system, so it was a complete replacement. We removed all wiring, conduit, control equipment, lighting. We left the existing submarine cables in place so we didn't have to go locate them and dig them up. We put in new control wiring, conduit, lighting, and submarine cables, replaced traffic lights, traffic gates, warning flashers. All control equipment was replaced. It wasn't up to code. And new motors and new motor brakes were replaced, were installed, but we left the original gearbox in place. So demolition and staging notes, there were quite a few plan sheets on this project, as you can imagine. One thing that I ran up against is our drafter actually retired during this project, so I had to do my own drafting as well. So it was something that was quite a lift for me. One thing, lesson learned on this is I could have shown a little more detail in a few areas. And there's some areas where I probably showed more detail than I needed to. But we worked through it with the contractor, and it worked out all right. But here's just one of the plan sheets where we're showing the contractor exactly what equipment's staying, what equipment's going, and where all the equipment's going to end up at the end of their install. Also of note, we anticipated the use of a backup controller and a temporary variable frequency drives, as well as a temporary electrical power source. But I'll talk about that in a second. The contractor used an alternative method that I thought was pretty neat. Here's just some more plan sheets showing all the detailing that we provided to the contractor, conduit routing, lighting details, full conduit schedule, all that good stuff. So design philosophy. This particular district, both the bridge crew and the electrical crew, they got burned a little bit by having complicated PLC control systems in place. I know those are used pretty commonly now, but being a somewhat remote region to Salem, where a lot of our support comes from, they wanted something that was really simple and could be maintained by their bridge crew and by their local electricians. So obviously we had to have a design that meets current electrical codes, has to meet AASHTO safety requirements as far as interlocking, safety interlocks go. So you can't operate pieces of equipment out of order. But we wanted to minimize the use of electronics and maximize the use of off-the-shelf control components, relays, lights, switches, that sort of thing. So getting into some of our initial conditions, here's the original 1931 load center. You can see some of the components have been replaced by electricians over the years. And there's the back of it. I call that the rat's nest. Good luck trying to troubleshoot that. It's quite a mess back there. See, it's just an open panel back there, not meeting any current safety codes. The original controller was designed by General Electric, and there's the original control console. It's a very simple design. And there's the original 1931 motors that were still working up until we replaced it. Again, the switch gear didn't meet any modern electrical standards. It would tend to throw off sparks as you would run through the gears, if you will. And in the back there, you can see the motor resistors that would go in series with the motor and give you your different motor speeds. The rotary cam switch I actually reused in the upgraded design. We were able to properly ground that, and it was already tied into the gearbox. There was no reason to design some new gearing to put in a new rotary cam switch. So I thought this was a fun picture. The bridge crew didn't like shooing away pigeons, so they took an old sign and put a box up there so the pigeons would stop sitting on those conduits, but they're already pretty rotten away. Everything was going to be removed. On the right there's a original conduit penetration through the grillage level subfloor there down into this counterweight pit. Those are the submarine cables at the top of that picture, which we cut them down as far as we could and left them in place in the riverbed. Here's some of the new equipment that we were installing. We did a full mock-up in the shop. Primary operator's console is there on the left. Originally, I had intended that we were going to use the original console and refurbish it. The contractor didn't really like this idea. There was likely lead coating on there. They didn't want to transport it up to their shop, so contractor worked with a local museum, so that's sitting at a local museum down there in Coos Bay, and they opted to build a new control panel. If I was building it from scratch, I probably would have done a different layout. Talking with the bridge crew, they've been able to just get used to the way this system works. And they say it operates just fine. There's some quirks to it because we kept the original control layout, but I think there's more logical ways we could have laid it out. And on the right there's just inside the control console where some of the interconnect wiring lives, and that wiring on the left of that picture is our temporary wiring where we mocked up the system, and we're able to check all of the wiring and interlock systems in the shop because it's much easier to fix it in the shop. Get it right there before you install it on the bridge. So again, this is the shop mock-up. On the left there's our safety interlock and control cabinet. That's really the brains of the bridge. That's where all the safety interlocks that keep you from operating equipment out of order. You got to make sure your traffic lights are red before you drop your traffic gates. All your traffic control equipment needs to be in place before you pull your shear pins out and get ready to lift the span, that sort of thing. And it's where all of the control signals are generated that are running your motor starters. And on the right there is our backup controller in a stainless steel box that is on the remote pier. Again, that was going to be used for temporary staging while they did electrical demolition, but you'll see in a moment that they didn't actually need it, but it's still there for any sort of maintenance where they would need to operate it from the remote pier. Construction staging. So this was their solution during construction staging, and I thought it was pretty ingenious. I'll show you how this works in a second. So this bridge was designed with a backup mode to lift it, being early days of using electric power to lift these bridges. They had an auxiliary shaft that would come up through the deck and a key you could put into it, and two people could just walk in a circle. It would take about 20 minutes to lift the bridge up, another 20 minutes to lift the bridge down. So what the contractor decided to do is they took that key and they built a copy of it that would go on a skid steer, the post hole digger, and they would spin that with that shaft engaged, and they could lift the bridge up. When I first started the project, we had a chip barge that was running pretty regularly through there, but they decided to start trucking their chips, and then the bridge really didn't get opened that much after the first 4 or 6 months of the project. It only got opened a few times, and then they had to open it to do work on the span locks, to do painting on the bridge ends, because the steel spans were also getting painted during the project. So here's what the machinery room looks like. And that auxiliary drive shaft, you can see there, extending up from the gearbox up to the deck, kind of at the center top of the photo there. So here it is with the new motors, motor brakes installed, all the conduit wiring is in. I have some more preservation work to do on the room itself, and then some protective screening that needs to go over the gearbox because we're still testing it at this point. Something else to note too, we didn't replace the machinery brake on the bridge. It was really integral to the gearbox, but we did replace the thruster, the fail-safe thruster motor. You could see that linkage. It actually extends out of the room, and the thruster brake is outside of this room. You can see it extending into the wall at the front of the room to the right of the gearbox. Submarine cable installation. During our in-water work period, it's a pretty simple operation. They float the submarine cable out, a diver goes down, trenches in with a water jet about 6 feet into the river bottom, and they guide those submarine cables into that trench. So that's what you're seeing there on the left. The right side is them hoisting the end of the submarine cables up into our motor control room, and I'll show you what those look like terminated here. So on the left is our operator console installed, and on the right is our nearly finished motor control room. 4 variable frequency drives are lined up there on the left side of that photo with their dynamic braking resistors up above them. For those of you not familiar with that system, most of the braking of the bridge happens through those dynamic resistors. The motor brakes themselves are really used as parking brakes or an emergency situation. And then in the back of the room there, you can see those termination cabinets for the power and control submarine cable, as well as the VFD submarine cables that are feeding the motors on the remote pier. So this is just some examples of our conduit wiring. We tried to be as neat as possible. Counterweight is up above on the left picture. We had to make sure geometry was correct so the counterweight wouldn't take out our conduit. Putting it down the counterweight where there's plenty of room made the most sense. On the right, we had to be real cognizant of how the truss moved and any interconnect wiring that went into the machinery room obviously had to go through a clear area in the truss, and you can see that in the top center, as well as some flexible fittings that feed the center channel lights and some of the limit switches for the span locks. The span locks were retrofitted with a hydraulic drive by the bridge crew, and they liked that system, so we interfaced with that system that was there. We didn't replace it, but we did put all new stainless steel plumbing in for them because the plumbing they had in there was in pretty rough shape. So this is pretty much the most congested spot in terms of conduit on the bridge. I worked with our structural designer to find the best place to get up into the pier houses, and coming in through the pier house framing here was a nice little spot where we could tuck everything in. It was a little hard for the contractor to pour that concrete back around it. They came back in the end with spray foam and kind of formed it up that way. I probably would have made a blank with some plywood and then fit the conduits in there, but it worked out in the end. And then there's one of our brand new stainless steel traffic gates that we put in. Came time to test the system. Remember when I pointed out those straddle bents earlier in the presentation? So soon after original construction, there was some shifting of the footings on this bridge. And it's kind of chicken or the egg, whether Pier 2 shifted first and pulled the approach with it, or whether the approach was pushing on Pier 2, but everything shifted. There was some loss of bearing area, and they had to put those straddle bents in place on those approach spans. But what that did is it would cause the Bascule span to bind up during certain conditions, temperature-based. Mechanical engineer tried to address this by redesigning the span locks, giving them some more play, giving them a bit of a flare so the span locks could guide properly into place. It wouldn't bind up when they were being pulled. However, it was told to us during testing that the bridge no longer bound up, and you could operate it however you wanted during testing. Well, we went and opened the bridge, and it caught opening. The motor torque went up. It lifted up the west span just a tiny bit, but then dropped it back on its bearings. Shook a little bit. It wasn't too hard of a fall, but we took that span up, did some more testing on it, brought it back down, and sure enough, it got stuck. So I'm getting calls from people saying, "You're all over Facebook. What are you doing? Why is the bridge closed?" So it took about an hour and a half with the guidance of the senior mechanical engineer to grind on those new span lock guides. They also brought a torch out from the local truck shop that was down there. He was nice enough to bring his torch up, and they cut away at it until they could get that back in place. This is really an issue in testing. The bridge crew, but they operate both spans now, and they understand you need to operate the west leaf first always, but typically operate both leaves at the same time, so you don't have this issue. That was a fun night. So we had a few adjustments we had to make. We had to make some adjustments to the cam switches, make sure our limits were set, so as the bridge lift, it didn't take out any conduit or walkways down below. We made those adjustments. There was one issue. It was somewhat a design issue, somewhat an ordering issue with the overspeed relays, and we had to add a little logic to take care of that, make sure the overspeed safety relays worked properly. There was a couple things we had to fix in the conduit schedule, but we worked through those with the contractor. Later, we had to come back and also make some seating adjustments. We were finding that we're overdriving the span into the live load shoes and storing some backlash in the gearbox when setting the brakes. So we had to make some adjustments with ramp rates and the VFDs and some limit switches to make sure we weren't storing that backlash when we set those brakes. But going back a bit, we did step through each process. Every piece of equipment, we measured parameters, we checked those out. The contractor submitted a full testing plan, really a checklist, and we went through each piece of equipment one by one, made sure everything was wired properly, everything was working as it should, checked those off one by one, and then we went through the whole process, make sure the interconnect wiring and the safety interlocks worked properly. And then we did these final test lifts with the contractor, final adjustments, and then the bridge crew had to go through, learn how to operate it, and operate it 10 times successfully start to finish with no issues with any of the systems involved before we closed out the project. Some lessons learned on this: we did this all with in-house contract management. We really had a great assistant resident engineer who really stepped up and took care of it, but this really specialized work. I think we really could have gone out of house and leaned on some consultant partners that have some more specialized knowledge in this, because that assistant resident engineer really stepped up, but he carried a lot on this project, and I think we could have used a little help here, but we ended up working with the contractor, getting everything done in the end, and bridge crew's happy with it. Bridge doesn't get open that much, but it's operating just fine now. So, any questions? No, that wasn't steel, kind of steel adjacent.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.